All right, this is emission of light. When we see emission of light, typically we think of what?
I think of light bulbs. We got
Yeah,
nice
light bulbs.
emitting light. Maybe the sun.
The sun is a good source. Yeah.
Fire.
Normally we think of like excited electrons, and so in an incandescent light bulb, did you guys see what the spectrum looked like? It was a complete rainbow, correct? And so inside, do you know what's inside an incandescent light bulb?
A metal wire that has electricity just going through it until it glows.
Isn't it tungsten?
Yeah, it's tungsten. Do you know why they chose tungsten?
It has a very high
Very high melting point. But the problem with tungsten is if you start heating it up, it's easy to oxidize. So how can you prevent tungsten from being oxidized?
When you put it in an incandescent light bulb, it's usually filled with, it's not filled with oxygen, right? Because that would oxidize.
Yeah,
It's usually
filled with
argon.
oxygen.
It's a vacuum.
Actually, it's not a vacuum because they don't want an implosion in there, and it will make it.
It's either argon or xenon. It's filled with.
Yeah, it's gonna be filled with inert gas. Sometimes it's not 100% inert. So sometimes what they do is they fill it with inert gas plus a halogen. And they fill it with a halogen because what happens is the tungsten gets very hot, it tends to vaporize the atoms off the surface. And when the atoms get vaporized off the surface, they'll coat the inside of the bulb. And when they coat the inside of the bulb, then the light output isn't going to be as great. And so you need to fill this with some kind of gas that won't. If you ever have a leak here and air gets in, then this tungsten filament gets instantly oxidized and makes a tungsten oxide ceramic, which is very brittle, and it'll break the filament immediately. And so you pass electricity here. So electrons go through, actually going back and forth. And so the electrons go through this and it creates heat, through, it doesn't move freely. There's some resistance because the tungsten atoms are vibrating. And so electrons have a difficult time, I guess, not too difficult, but a difficult time navigating that path, depending on how good of a conductor it is. And so there's a little bit of resistance, and it generates heat, and everything gets hot, and eventually it gets so hot it starts to glow. Initially it'll glow red hot, It glows red hot. Well, actually, initially you can't even see it because initially it doesn't grow red hot. Initially it grows infrared hot. Infrared because you can feel it, but you can't see it. There's heat coming off that tungsten. And so when it's going infrared, that means it's absorbing this amount of energy, and then it doesn't stay there forever. It drops back down and then emits. So we have absorption of energy. In this case, it's not absorbing infrared light. It's just absorbing energy from all these vibrations. It's kinetic energy. And that's going to be converted into light here when it drops back down. When it drops back down, it emits, let's say, IR. IR is long wavelength. And then as it gets hotter and hotter, then we start emitting, red light, and then orange, and then yellow, and then eventually it's going to glow white hot. When it's glowing white hot, then what colors are we emitting? All colors of the rainbow. And so that's it. Now, when we look at tungsten, tungsten's a metal. In metals, the electrons are loosely held. And so the electrons are relatively free in tungsten metal. So these are this is tungsten solid. And the electrons are free, they have mobility. They aren't completely free because, they're confined to the metal unless you knock the electrons off the metal. But that's it. Well, we heat things up, so if you put a piece of tungsten metal on the flame and you heat it up, it'll start to glow white hot, unless it becomes oxidized. It'll probably become oxidized. and then stop the line. But other elements will give some characteristic colors. Like, for example, this looks like a flame that doesn't have enough oxygen, or this looks like a flame that has sodium in there. Because sodium gives off a characteristic. What color is the sodium? Kind of orange. Orange, yeah. So sodium lamps like that, are really efficient. These used to be the most efficient before LED. And so a lot of old street lights, if they're still around, use sodium lamps because it doesn't take much electricity to excite the sodium atoms to get them to start emitting. But why is it that sodium doesn't emit the full rainbow? Even if you crank up the power on those, you aren't going to see the white light. You're just going to see orange light. Why is that? And then we see the different elements that give different colors here. This is all emission. For example, hydrogen. If we look at the hydrogen, I don't know how many of these you saw. I think everybody sees the red because that's the most intense, the brightest line. And then the next one, this is supposed to be green, but it may not look green to you, but this is in the green region. Green is actually a spectrum of greens. We have greens that vary from yellow to blue. And so this is maybe more on the blue end of the green range. And so we have this red line and this green line. Although the green line looks to be the most intense, it's not. The red line is the most intense. And we could detect how many photons are striking the detector. And if we detect how many photons are striking the detector, this one's going to be a lot more photons. And so in the old days, they just used to measure how intense this line is. And nowadays, we can just measure how many photons hit the detector and then see how big the peaks are. So this would be the biggest peak, and then this would be a little smaller. This is the green, and then this is actually, it looks violet, but this is the blue line, and then this would be the violet. These are becoming a lot less intense, like this one. A lot of people will only see 3 lines. How many did you guys see? 3 or 4?
Yeah, max 4.
Yeah.
Okay, only 5 in blue.
This 5th line here is going to be very faint. It's going to be hard to see for a couple of reasons. One, it's less intense. 2, it's really at the edge of what we can see. Because this is around 400 nanometers, so we can only see about 390. And so we might not see this one at all. So normally we just see 4 lines in the visible spectrum. And this one would be kind of approaching not violet, but it'd be approaching what's beyond violet, ultraviolet. And so this would be approaching ultraviolet. We got to watch out because even with a like this tungsten filament, this can emit ultraviolet too if you get things excited enough. But a lot of things absorb ultraviolet, like the glass. The bulb would absorb ultraviolet. And then ultraviolet is divided into different ranges, UV A, B, C, just to split it up. We don't do that for like green, green A, green B, green C. But ultraviolet, they do it. All right, that's when you excite things. But, as energy is concerned, we can excite things like this and have them emit light, or we can have what's called an absorption spectrum. That is, if we shine a rainbow, let's say we shine white light at hydrogen atoms, the white light gets absorbed. So we'll have an absorption line here. So this is called an absorption line. This is called an emission line here. We'll have an absorption line in the red, an absorption line in the green, absorption line, it's borderline. Absorption line in the blue, and absorption line in the violet here, and close to the ultraviolet. We'll call this violet as well. This is going to be exactly at the same spot. And so we could either do emission, where we excite things, and then see what colors of light, or we do absorption, where we just shine light at it and see what colors it absorbs. These are very sharp lines indicating that, there's a very specific energy. We were talking about the resonance, the very specific energy. Like the sun emits all colors of the rainbow, but when we look at the spectrum, the solar spectrum, there are some colors missing. You see these lines here, the black lines means those colors are missing. Those colors are missing because those elements are present either in the sun or before they hit our detector on Earth. And those get absorbed from there. And so this way they can tell what elements are present. Because you'll see the absorption lines of hydrogen in the solar spectrum. I don't know, it's probably hard to see when you went outside with those. All right, so what are we doing today is this. Today we're looking at food color. Actually, it's red food color. There's lots of different red food colors. But this red food color is not really red. This red food color is violet. And it's got the name methyl violet. If you want to see the formula is kind of big. It's an organic compound. And so what we want to do is we want to know, is it methyl violet? Somebody confirm that? I forgot to bring my lab manual.
What experiment is it?
This is experiment
2.
Oh, this is
No, 4. I'm not 2. 4. Is it 4?
yes. Oh, Boston.
Oh, erythrocene B. Sorry, it's not methyl violet.
I'm not sure how you're supposed to say that. Professor,
Yeah.
how do you say it?
Erythrocene B?
Erythrocene?
Yeah.
Thank you.
Erythrocene, or was it sin?
Yeah,
S-I-N.
I'm not sure how you're supposed to say that.
Yeah. It's well, I'm sure there's lots of different pronunciations.
I just can't pronounce a lot of things.
Okay. All right. So, what color is erythrocene supposed to be?
Red.
Red. It's
Red number 3.
red number 3. Now, erythrocene is not an atom; it's a molecule. With atoms, you get absorption lines, very sharp lines. With molecules, we get absorption bands. The reason is this: in molecules, you have vibrations, and when you have vibrations, that changes the energies, electrons. So let's say it vibrates out, maybe the energy goes up, it vibrates in, the energy goes down. And so the energies are fluctuating a little bit. And so what we don't get are sharp lines. And so what we're going to look at here is we're going to measure part of the UV. So this is called UV vis spectroscopy. So we're going to shine a little bit of UV on there and see what wavelengths of UV light are absorbed. UV is in the 1,000 nanometer range. And then we're going to shine visible light, which is in the 800 to 400 nanometer range roughly. They say 760 to 390. So we're going to shine some visible light on there, and we're going to shine a little bit of ultraviolet and see where it absorbs energy. And so this will answer the question, if it's red, what's causing it to be red? So if we look at the color wheel, red, orange, yellow, green, blue, and then indigo violet, we put together like this. What's causing this to appear red? Well, one way it could appear red is if it absorbed every other color in the rainbow except for red, and only red light can pass through. It's going to be a solution. We're going to make an aqueous solution. So if only red light passes through, then that's all you're going to see is the red light, and all the other colors are absorbed. Another way that we can produce red is how? Yeah, if we absorb green, then all the other colors are going to average out to red. Or if we, Yeah, blue and yellow will average out to red, etc. And so by measuring the spectrum, we can see where it absorbs because it'll give a quite a different spectrum. And the spectrum is going to look like this. What we put here on the y-axis is absorbance. And then on the x-axis, we usually put lambda, or the wavelength. And since we're working in the visible and ultraviolet, we usually use the units nanometers here for the wavelength and not meters. And so here we can see, if we're in the UV, we'll put it out here. I don't know which way we're going to do this. If we're going to start at red and go to UV, or we're going to start at UV and go to red. I have to take a look at the spectrum again. But nonetheless, if we go from low energy, actually, if we're going lambda, then we're going to go from small wavelength. So we're going to actually start off with the highest energy. It'll go UV to violet, to indigo, to blue, green, yellow, orange, red. IR, unfortunately, our spectrometers won't be able to measure IR. And so it's just going to end at red, roughly. So if it absorbs all the colors, what we see is an absorption band, except for red. And so this absorption band just means all of these colors are absorbed. If it's absorbing it in green, then what we'll see is an absorption peak around green, somewhere around green. And that would cause it to be red. And so we're looking for absorption peaks, absorption bands. For molecules, again, we don't see absorption lines. We don't get those sharp lines that you guys saw on Monday because of all the vibrations, whatnot, for molecules. And so we just look for these bands. It turns out it's pretty easy to measure the spectrum. So why don't you guys check out the equipment? And then we're just going to go through it together because there's some changes in the procedure. And so we'll just do this. You're going to work